today who will tell us about a subject which is new to most of us, stochastic kinetics of magnetic molecules. Artur Maksymov.
Okay, good morning. So first beginning my presentation. My name is Artur Maksymov. So first beginning my presentation, let me introduce a bit myself. I have successfully graduated PhD studies at Centrum University in 2012. After this, it is also my own matter. After this, I had two postdoctoral positions, one in Iași in Romania at Centrum University, and second one at University in New Orleans in the United States. My main field of research is stochastic non-equilibrium phenomena in magnetic molecular systems, namely in spin-crossover compounds, a kind of molecular magnet. Also at the University of New Orleans, I have having deal with magnonic crystals that I studied in the framework of speed wave theories. But today I would like to talk about stochastic kinetics of molecular magnetic systems. Usually, magnetic properties is associated with ionic or metallic lattices, but in the recent decades, in the scientific communities are focused on the magnetic molecular materials that in better ways realize the principles of informational nanotechnology that claims one molecule, one bit of information at minimal energy consumption. From this point of view, molecular magnets are very interesting for studying. Molecular magnets are a class of materials with molecule-based magnetic properties. The principal characteristics of molecular magnets may be following: slow relaxation of demagnetization that may be of polymolecular origin, single molecular unit can be magnetized in a magnetic field, and that will remain magnetized even after switching over the magnetic field. No interaction between the molecules is necessary for magnetization. It is intrinsic property of molecule. Single molecule may be dissolved or located into a matrix, and the magnetic properties will be kept. One of the most perspective class of molecular magnets are spin-crossover molecules. This is a class of inorganic coordination complexes with process which is characterized by D4, D7 electronic configuration of outer orbitals of a metallic ion which is situated in the center of the environment with octahedral symmetry. And this kind of molecular magnets is possible. This is by stable materials, which is characterized by two stable states: low spin with low spin configuration and high spin configuration. Between these two stable states is possible the transition that are induced by light radiation, temperature, magnetic field, and other physical field. These spin-crossover compounds can be exist in as 1D, which forms spin-crossover chains, 2D, which form the 2D lattices, 3D, which forms the crystal, and the most interest has the spin-crossover compounds of 2D and 3D, which can be easy have a potential practical application. In this work, we are focused on the spin-crossover compounds with the ferrous plus metallic ions. This spin-crossover compound is characterized by low spin state with total spin number s equal to 0 and high spin state with total spin number s equal to 2. Between spin configuration and the interconversion take place. Here you have the interconversion that take place. It is induced by light radiation. The so-formed high-spin states, the schematic formation of high-spin states by light radiation is shown on the figure on the left.
But what kind of material it is? I mean, you are talking to people who understand a lot of physics, but not details of your particular field. So I have a feeling that it would be better to slow down and explain somehow in more details.
Okay.
What kind of material it is?
It is molecular materials which can be characterized by magnetic properties, and this is non-metallic ligand, which in center of which is situated the ionic metal, and this coordination compound. This coordination compound material.
How far is it from ferrofluids, these materials?
Well, it's inorganic. It's inorganic, and well,
What does it mean that it is organic?
it's non-organic.
Non-organic.
Non-organic, yes. Well, on this slide is shown the high-spin state may be formed by light-induced spin state trapping, and then an equilibrium population of high-spin state is growing in this way, and high-spin state can be transformed back into low spin by if the potential barrier between these two states is overcome. Also, the high-spin state can be transformed in a low-spin state by light radiation with the lower.
Yeah, but excuse me. So there is this. The problem is that
Here?
yeah, this is this compound, right?
Yes.
Those rings, and electronic configuration is such that it admits two basically semis. Well, ground state can be only one in quantum mechanics. So two closely separated states, one of high spin and one of low spin, or
Yeah, the problem is that if we put metallic ion in ligand environment, this ligand environment form the octahedral splitting. It splits the d orbitals into sublevel and appears the additional sublevels where it can be populated in different way by Hund's rule. And depending on this value of ligand field splitting energy, it's possible to have the different spin configuration. And this ligand field splitting energy may be controlled by external field, like light radiation and temperature and others.
So what is, here we have the ground state, and then we have various excited states. What are typical lifetimes of these excited states? Because they are certainly not stable.
At very low temperature, this lifetime of metastable state can practically it has few days may have, but theoretically it can live virtual infinity long.
No, it cannot live because it's not a ground state, so there must be a transition to.
But this transition between this high-spin state to low-spin state is forbidden. Usually it's forbidden, and at low temperature it can live very long.
Well, when you say it's forbidden, that means that it's forbidden if it is supposed to be subject to the dipole radiation or something like that. All these forbidden states usually are allowed when you allow for transition, etc. There must be some transition that is allowed, even though the name forbidden would suggest that cannot happen. I don't believe that you can have a stable state which is not the ground state. Because you always have interaction with virtual photons which will cause the transition. I understand that the lifetime is very long.
favorable location of electron on d orbitals is this one, according to Kunz rule. So this, if we keep this ligand field splitting energy high, being low, this high-spin state will live a pretty long time.
Well, but there is always tunneling or some kind of transition which will cause the decay.
Yes, of course. I regard this decay in the terms of stochastic terms. On the next slide, I will show how we analyze this kind of things. Okay. So usually, these metastable states theoretically can live infinitely long by due to interaction with environment. It is decay, and the kinetic equation of decay of metastable state is given by equation 1, where EA is activation energy of decay. In this way, if you take into account that high-spin state is induced by light and taking into account the relaxation, the kinetics of spin crossover compounds can be described by the equation 2 in terms of concurrence flow of the excitation and the relaxation. This equation can be analyzed by dynamic potential in terms of Platonov function.
No, but you have repeated again that theoretically this state should live for infinitely long time. I mean, I'm sorry, but that means that cannot be, because you know, if forbidden states in quantum mechanics of atoms or molecules are forbidden for certain transitions. If you expand e to I k dot x into the Taylor series, the first term doesn't contribute because they are orthogonal. The second term may not contribute because of parity, whatever you like, but you certainly find a 157th term which has a non-zero overlap integral, and although this integral can be very small, in principle it is non-zero, so there are no such states which are in principle theoretically excited states which are in principle theoretically stable. I mean, it would be a Nobel Prize discovery if somebody could find something like that, because it would be the first example of a quantum system which has a double vacuum which is not uniquely defined.
Well, I think there's an analogy with the radioactive decay. There are cases where the lifetime is years, and I think
sure.
this is, so this is something like this. So it could be very long on any reasonable atomic scale.
Yeah,
Like we
that's
said,
true.
the days, right?
Yes, and this is a macroscopic approach we didn't take into account right now, microscopic process and molecule, just regarding this at this moment.
No, but even in the absence of also in the absence of external effects or external fields, this atom, this molecule is embedded in the vacuum, which is a medium by itself, and that can generate spontaneous transition, right? And so, but I understand what you want to say, but I think, okay.
So here is showed the short analysis, analysis of dynamic potentials. Mostly is shown the case A and C corresponds to the boundaries of bistable region, and case B is intermediate. By first derivative, it's possible to analyze the fixed points, fix the stationary states of the system. So monetization.
Excuse me, and what kind of potentials they are?
Dynamic potential, which you analyze it in terms of Platonov function. This one.
Okay.
So, taking into account the interaction with the environment, the spin crossover compounds, and it is better to describe by as particles in the velocity in the random velocity flow, which is possible to describe by differential equation 3. General form is this equation is given by 3. The function U is consisting of the deterministic component and of random, by random component. We are taking the one-dimensional case where stochastic process is linear, and in this way we started our dynamics by Langevin equation 4. Here the stochastic terms is considered additive if amplitude function is independent of time and is constant, and multiplicative if this amplitude function depends on time and on system variables. To solve this equation means to characterize completely the stochastic process X, or to give, which means that we can obtain the n times probability density function, which will be characterizing.
And stochasticity in this G means what?
This is fluctuation, just random fluctuation. I will define this process on the next slides. But G is the amplitude function of noise. No, amplitude of noise of this stochastic term, and it may be additive or not.
Yeah, but stochastic means that what, correlations at two different positions are zero or something like that.
Yeah, I will define it on the next slide. So here I would like to present the definition of stochastic terms. If X is a random walk process, the stochastic process may be defined by equation 5. Taking into account that this random walk process is Gaussian, the stochastic process will be Gaussian too, and in this way it is possible to be defined by the correlation, by mean value and correlation function given in general given by here. I'm sorry, I will just. Now, if you tense the epsilon to 0, the stochastic process becomes the derivatives of random walk process, and then the correlation function becomes a delta function. In this case, if we tense the number of steps to infinity and the times of every steps to 0, the random walk process tends to the Wiener process, and the derivative process tends to the white nose process. In this case, the white nose process is a Markovian Gaussian process, which can be described by the mean value correlation function given by 6. And the white nose process can be considered the derivative of the Wiener process. Generally, it may be presented as may be understood as a series of impulses with very infinitely short time and very high amplitude. So in other words, it's maybe described as a series of delta functions. In order to characterize, due to this stochastic process is a non-linear function of time, is a non-continuous function of time, it is impossible to derive, the Wiener process is impossible to derive. In this case, we need to use some interpretation, its interpretation. The most widely used interpretation is to describe the stochastic process is Ito or Stratonovich interpretation. These two interpretations are statistically equivalent, and the difference lies in the describing of function of amplitude of noise G, where in Ito interpretation it is taken at the beginning of the time step, and in the Stratonovich interpretation it is taken in the middle. We used the Stratonovich interpretation for our calculation. In this way, taking into account the possibility to describe the molecular magnetic materials which interact with the environment by stochastic differential equation, we use this approach and describe our spin crossover compounds by equation A, which is Langevin equation, with where C is Gaussian white noise. To this equation can be put in correspondence the Fokker-Planck equation, which describes the evolution of probability density function. In general, this Fokker-Planck equation which is given by equation 11 has no analytical solution, but in some approach it's possible to be derived, and the stationary solution of Fokker-Planck equation 11 is given by equation 12. This equation 12 is the probability density function which can characterize the stochastic differential equation 10 in the stationary case. It must be noticed that correlation time of autocorrelation time of noise it can be very small, but in the real system it can be zero. In this case, we need to have to take into account the non-zero correlation of noise and the stochastic dynamics of the spin crossover compounds may be described by two-dimensional Markovian equation, which is presented on the right upper corner. If you solve this equation, these systems of equation, we get the equation 13 that describes the dynamic of spin crossover compounds and the general magnetic molecular system at microscopic approach in the presence of colored noise action. We evaluated qualitatively mostly. We evaluated the escape time from a stable state of the compounds in Kramer-Slack approximation by equation 14, and some results of this escape time from metastable states are given on the figures. Here the metastable is the low spin states, named the left one, which is shown here, and stable is the high spin. Up to now, we are considering considering the stochastic dynamics, which has just only one stochastic terms, which was described by additive noise, and but it makes sense to also to study the possibility of fluctuation of control parameter with beta from the dynamic equation. In this case, the stochastic dynamics will be described by, in the case of fluctuation of control parameters, the stochastic dynamics will be described by equation 16, which contains two noises, additive and multiplicative noise. This equation was reduced to the equivalent differential equation with one multiplicative noise and with effective amplitude. This equation is given by 17.
Okay, but at the beginning we had a more or less clear physical picture. There was a certain inorganic molecule, metallic ion inside, and there were energy levels and so on, And now we are analyzing
the microscopic approach.
Sure, but where this noise physically comes from?
From the interaction with the environment. We model this interaction as the interaction with feedback of the material, microscopic material.
Okay, but what is the assumption? I mean, what does it mean that it is multiplicative? I mean, physically for this environment?
In the more rigorous approach, it is better to describe the dynamics by equation 16 because, the nature of noise is temperature. This noise has temperature nature, and taking into account the interaction which exists in the materials, it's impossible to take into account just on the background noise, because the noise, in some way, this oscillation, this fluctuation, which is characteristic for each particles, are correlated within themselves. So it depends on the system variables. Here, the beta is a control parameter that that describes the light induced. That describes light radiation. And in this case, in this assumption, we.
But let me ask further. This what is the physical picture? I mean, this molecule is then put inside some lattice of some material, or
Yes, this is a crystal.
you put it in the crystal. So the heat buffer is the rest of the crystal, basically, right?
Yes.
Phonons.
Phonons.
Well, yes, like this.
And are there some data about, perhaps they are, about the lifetime or decay of this semi-stable states?
In
So
general,
your goal is then to compare yourself with what? Or to derive what kind of characteristic of this system?
we studied mostly the hysteresis behavior. I will show it on the next slide.
Because from the point of view of application, which feature of this metastable state seems to be most desired? Because I understand that one idea to perform such a study would be to derive properties of ideal material, which would then best serve this kind of molecular quantum informatics, right?
Well, it's maybe not quantum, but in information technologies.
Yeah, exactly. So what?
The idea is to have a very long lifetime of metastable state, which give us the opportunity at high temperature, because at low temperature is pretty long. It lives pretty long. Some experiments showed living.
So resistance against this heat buff interaction, right?
Yes.
In that
Yes.
sense.
So the main purpose is to have something that would store information
Yes, of course.
in a stable way.
Yes, yes. Because right now at low temperature,
So
very low
this molecule is your qubit,
Yeah, in a sense.
because it has two states.
Yes, yes, yes.
So it is a qubit.
So here is presented the state, the phase diagram in the dependence of additive noise intensity and correlation between the noises. This state diagram describes briefly the possible state of the system, which may be for different possible states. The states with where the low speed state is stable and just only it is presented in the system. Here is the region where is possible the stable low speed states and metastable high speed states. Here is here is metastable low speed and stable high speed. Here is stable low speed, metastable high speed. And here is just only one state is presented, high speed state.
And what are the experimental data that are to be compared with your results?
Concerning this kind, well, I have some experimental data, but I did not present it in this presentation. Related to this phase diagram, unfortunately, there are no experimental data. It's mostly theoretical and just to analyze the possibility of state realization of the materials. But concerning the data which I will show on the next slide, concerning the hysteresis, where we derive the hysteresis. So there are some experimental data, but unfortunately I must know that I will not include it in this presentation.
But what kind of data, just in general terms, what kind of experimental data are to be confronted with your theory? What is being measured in these components that can be explained by theory?
The width of hysteresis, the hysteresis width. Well, I mean, related to this phase diagram or what?
No, in general, concerning your
Material.
material. You have some experimental data that can be compared with the results of your calculations.
Well, the data is, there exists some experimental data, but it's not provided by me, but in literature there are some scientific groups, for instance, which studied these materials experimentally, and they showed the wide hysteresis loop of this material. And we try to reproduce this hysteresis loop using this theory because the existing theory cannot give it doesn't show hysteresis, the microscopic.
But the hysteresis when it comes to magnetization.
Yes, hysteresis independent of
Magnetization.
control parameter temperature or light. So yeah, the output parameter we check the magnetization of the materials, but this magnetization can be controlled by temperature or by light radiation. Because this high-spin fraction from here, HS, is the fraction of my high-spin molecules. But also the fraction of magnetized molecules. The molecule which is in the high-spin state.
No, so obviously magnetization is destroyed by temperature, right? And this is, you're trying to predict.
Well, yes. It's destroyed by. Yes. But in this way, in this case, temperature can, if it is pretty low, it can contribute to the magnetization theory. So temperature can introduce, can decrease the ligand field splitting energy and to populate the high-spin state. I will show this on the when I go to the microscopic description of these materials. By equation 18 we are calculating, we are numerically solving.
What, how, because typical hysteresis is more or less measured in such a way that you magnetize the material by applying magnetic field, then you reverse the magnetic field, you demagnetize it, then you magnetize it again by the same field, but you get a different magnetization, and this is how this, it is not, you do not, well, everybody knows what is hysteresis. Now, how you do it with light, you induce magnetization by interaction with light, I understand, because you move electrons to a different state, and then how you demagnetize it and magnetize it again, how is this made? Hysteresis with light.
The demagnetization from high-spin state, the demagnetization, which means the transition from high-spin state to low-spin state, can be also induced by light, which that it is shown on this diagram here. So the populated state may be very fast converted into low spin state if you radiate it by light with certain wavelength. And I mean, what happens really in the molecule?
In the experiment, when they try to find this hysteresis, isn't it done by classically? I mean, by changing external magnetic field. Just
Yeah.
they check this hysteresis by external magnetic field.
Yes. Here the hysteresis are not depending, or is not in magnetic field. It's temperature induced hysteresis. Is in temperature hysteresis, and in light radiation.
So in general, hysteresis means that at a given parameter, you have two values.
Yes.
Right? And this parameter of yours is temperature.
Yes.
So at a given temperature,
I can
you can have two different
Yes.
magnetizations depending on previous history.
Yes. Right. I will show you on the next slide. So this is in this way we compute the stochastic differential equation. Here is presented the probability density function for different noise level and correlation. In these pictures analyze the role of additive and multiplicative noise. And this way the role of additive noise suppresses the potential barrier, whereas the multiplicative noise can induce the transition. Up to now we are studying the spin crossover system in macroscopic approach by differential equation, but also it makes sense to study it at microscopic approach. Well, maybe not mostly mesoscopic approach. It's something because it's not strictly microscopic. The idea to study these materials at microscopic approach lies in the specific of transition of these molecules, which change in volumes. So the high spin state has the molecule in high spin state has a larger volume than low spin, and this induces additional interaction in the system, and it can change the macroscopic behavior. So at the microscopic level, the transition between the high spin and low spin states can take place if the ligand field splitting energy is close to the spin pairing energy of the electrons, and in this way the electron will move from the T2G configuration to sublevel to EG sublevel, which are shown on the upper picture. And in this way we get the high spin state. In the point charge model approximation and for perfect octahedral symmetry, the ligand field splitting energy may be described with the equation 24. The materials as a whole, the magnetization in the materials as a whole may be described by classic Ising model. This model can be applied for spin crossover compound with several restrictions. First of it is that the external field cannot be zero, whereas in the classical Ising model it's possible to be zero. This external ligand field, the external field is an effective field, which is described by the action of ligand environment on the metallic one, and on the it also includes the external physical field like temperature. The effective field for spin crossover compound is described by equation 26. Here, the first term in this model describes the interaction between the spin crossover sites. So the parameters which define ligand field splitting energy cannot be precisely can be defined precisely, and in more rigorous approach, it fluctuates in time. This leads to the situation when the effective field also fluctuates, and in this case, the Hamiltonian of Ising-like system, Ising-like model which describes the spin crossover system, takes the form 28. In the simplest case, this fluctuation can be described by a simple Gaussian process. white Gaussian process with the correlation function and the mean value defined by 29. In most rigorous approach, we need to taking into account the non-zero autocorrelation time, which means that we need to describe the correlation by Orsten-Olenberg process, which is a colored, which is colored. The correlation function of Orsten-Olenberg process is described in the equation 30, and the power spectrum of Orsten-Olenberg noise is given by equation 31. Here is important things is that this power spectrum is inverse proportional to the correlation time tau, which will solve. Also, taking into account the existence of interaction between the spin crossover sites, the fluctuation of every sites cannot be regarded just only correlated in time, but also it is correlated in space. The space-time correlation of, in this case, the spin crossover sites can be described as a collection of harmonic oscillator. This noise environment can be described as a collection.
Well, now you have sites, so there are many such molecules.
Yes. Yes.
Where do you have these harmonic oscillators with the first order equation? Here. So psi is the
Noise for different, the fluctuation for different sites.
yes, but where is the harmonic restoring force? Somehow I don't see the connection with harmonic oscillators.
It's not direct connection, it's more approach. You use
No, harmonic oscillators means that something is oscillating periodically with time.
Those are rather
The
follows.
second
I think.
term is just.
No, because this is equation, first order equation.
Is psi the analogy of position or the momentum?
Psi is the momentum of the
But then if it's momentum, then it should be on the right hand side the position, not the momentum.
Something is. At least we don't see any harmonic
Yeah,
oscillation.
that's what I said.
check this equation carefully. Anyway, we described the fluctuation, correlation, the space correlation in the system by equation 32. Using the Metropolis algorithm for simulation, where we define the probability transition by equation 33, we simulated the behavior of this system described by Eisenberg Hamiltonian. The relation of fictitious spin, which is in the Hamiltonian, and with the macroscopic parameters high spin fraction, is given by equation 35. We use these parameters for simulation, and here is presented the results of hysteresis width for different boundary condition. The black line is the dependence of hysteresis width on the system size for periodic boundary condition, and the red line is for free boundary condition. Here are presented the results are presented the hysteresis for a different case for different fluctuation and for fluctuationless case. The black curve is for the system without fluctuation, and for this case is the interaction between the site is chosen in such a way that the hysteresis is unnoticeable. When we introduce the fluctuation, the hysteresis enlarges, and as you can see, for colloid fluctuation, it's become narrower, but the space-time fluctuation enlarges again very much, which is presented by the pink color. Here we are studying the transition for in the second order phase transition regime. We are choosing the interaction constant in such a way that the fluctuationless case gives the second order phase transition, and the presence of fluctuation, which corresponds to the red curves for white fluctuation and pink curve for space-time correlated fluctuation. Presence of fluctuation leads to hysteretic behavior of the system. Here is presented the spin configuration during heating process. The figure A is for case without fluctuation. Figure B and C is for white and space-time correlated fluctuation. On these pictures is shown the evolution of the system for 3 different cases. As you can see, in the case without fluctuation, the high spin fraction fluctuates around its equilibrium value 0.5. In the case with 5 fluctuation and the space-time correlated fluctuation, we can show the transition, which for space-time correlated fluctuation is more drastic during heating process. On this slide is shown the dependence of global coupling of hysteresis width on global coupling and autocorrelation time tau. As we can see, the global coupling and autocorrelation time is inverse proportional, and act on the system, its action on the system was the opposite. Here we are studying the number of sites. We obtained the histograms, which describes the number of sites at a given fluctuation value. For white noise case, which corresponds to the background gray. For the colored noise, which is described by the blue histogram, and for space-time correlated fluctuation, which is described by the red diagram. As you can see, the correlation of increasing of the correlation time narrowed this histogram, and for space-time correlated fluctuation, it can be moved between those. So here we will present some summaries. So the behavior of light-induced speaker source system was studied in terms of dynamic potential, by dynamic potential in terms of lateral function. It is established that the change of self-acceleration factor can affect the stable properties of the system through the change of metastable state, when the control parameter beta, which corresponds to light radiation, change the potential as a whole. By analyzing the state diagram of spectroscopic components built in the plane of additive and correlation, additive noise and correlation coefficient, the boundaries of bimodal and unimodal regions of the system were established. It was established the behavior of changes of probability, density function, distribution of speaker source system states depending on variation of additive and non-additive noise intensities and correlation coefficient between them. It was shown that the additive noise suppresses the potential barrier, whereas the non-additive noise can induce the transition. In concept of breathing crystal field, speaker source materials in framework of using like Hamiltonian has been in the concept of breathing crystal field to speaker source materials in the framework of using like Hamiltonian has been applied. the essential feature of the model is the existence of external crystal field of random statistical nature. By using Monte Carlo simulation, we have computed transition curves for different external field without fluctuation, with light fluctuation, with color and space-time relative fluctuation. The action of fluctuation decreased the threshold spin-spin interaction of the first order phase transition. Also, we have shown that the effects of fluctuation are more evident for small system, and the increasing of the system size reduces the influence of fluctuation until the saturation regime is not reached. So here is some reference.
In a phenomenological approach of yours, I think it's absolutely necessary to have some idea about the values of the parameters, which must be taken from experiment. So what are the experiments that can serve here to provide the values of all these coefficients? For example, in your Ising model, you have the coupling constant J. How big is J such that it would apply to realistic systems?
Well, J is mostly maybe related order than the.
So what are the experiments that you really have
The
in mind?
real experimental J is around 150, 300. The values of J is from 150, 300.
What about all these other parameters? Where do you,
Delta is taken from for real this is relative splitting
in what units this?
This is joule, if I'm not wrong.
In what units?
Joule, if I'm not wrong.
In
No, in units of
joules?
No, I'm sorry, it's in units of temperature.
KBT.
One thing which here is
And again, the spin-spin interaction J's, in what units? You didn't mention any physical units here.
this is Kelvin. Taking into account that we take the Boltzmann constant equal to 1. In this case, all these units is in units of kBT. KT. Kata.
In KBT.
Yeah, very short.
So it depends on temperature.
Yes.
So your units vary with
No.
temperature.
No, everywhere delta comes divided by K. Okay.
KT,
So,
no? Then it depends on temperature. So that's
it cannot be because there wouldn't
Cannot
be
be because the
any
energy-
temperature dependence.
yeah, the energy gather cannot depend on temperature.
Yeah, I think the other way of rephrasing Professor Bieński's question is, what have you learned actually? What kind of, how this optimal materials from your point of view should look like? Because it's very easy that to say that certain type of noise preserves this hysteresis, or which is probably what you want to achieve, the permanent magnetization, better than other, but what does it mean in terms of material?
Noise in terms of materials?
No, what does it, yeah, I mean,
Real.
because your presentation had clearly two parts. First one was referring to a certain materials, a certain physical situation, and certain technology, promising technology. And the second one, in particular this Monte Carlo, is just a simulation of a Monte Carlo with the presence of noise. And that the hysteresis is there is not a surprise. I did such a simulation without noise, and there was a hysteresis, temperature hysteresis there. And basically, I miss the link between the two. There's a certain model which has a certain property, fine. What have you learned about those materials from that?
The possibility to have a hysteresis induced, well, controlled by some way by noise. but the noise itself may be described by the structural disorder of the lattices. It's at the same time.
Yes, but then which kind of structural disorder? This is the point. I'm not sure. Basically, is it right to say that if you would summarize the influence of the noise on this hysteresis, is there a particular type of noise which somehow preserves this hysteresis behavior better than other, or?
When you construct such material, what should you avoid and what should you insist rather than?
Well, this is a theoretical assumption, of course, and well, we just at this moment we just trying to see how the noise, how can be the role of noise in the material. Because the idea is to construct a theory which can describe the real hysteresis. Because the theory without noise can show the smaller hysteresis that it's possible to see on practice, on the experiments. And right now it's not very so strict approach, but it's just an attempt to describe the approach a bit more at the real situation. It was the aim of this study.
More questions? If not, thank you.